All right, let's look at resistors. So at the end of class, as was indicated on the board when we first walked in, you have a failing marker. So if I have a, say, 12-volt battery and a 3-ohm resistor, I know that I'm going to gain 12 volts, lose 12 volts, so that I end up back at 0 by the time I get back to my path. Kirchhoff's voltage rule, or loop rule. So if I'm going to lose 12 volts going across here, going in that direction, then from Ohm's law, I can figure out the current flowing through across there, and so we end up with 12 is equal to I times 3, or I is 4 amperes. The minus sign disappeared, in fact, that I know that when I'm going with the current across a resistor, that I'm going to lose potential. So it's already that if I wrote down -4 amps, that means, oh, it's going the other way. So we've already built in this concept that with the current, potential drops across the resistor. Now suppose instead, I have a 3-ohm resistor and a 4-ohm resistor. What now? Well, I know I'm not losing 12 volts across either of these specifically. I'm losing 12 volts across the whole thing. I'm going to lose some amount of voltage here. We'll just call this V3, delta V3, and we'll lose some voltage across here. However you want to play with the negative signs. So I need to somehow combine these two. Well, if you recall, resistance, rho L over A, where this is the resistivity of the material. L is the length of the wire, and A is the cross-sectional area of the wire. So if I have a wire, let's just say that long, I can measure the length. If I know the value of the material, you can look up what the resistivity is, use micrometer to figure out what the diameter is to solve for the cross-sectional area. So I can treat this as one long resistor, or I could take this wire, insulate it, wrap it around into a tiny little space, put a shell on top of it so that it's hard, and I've got one of the resistors we have upstairs. Or I could just break it in half. I could just treat it as two different resistors. So if this is L1 and L2, where L1 plus L2 is equal to L, the original length, then my resistance, my total resistance, is not going to change just because I'm treating it as two separate parts. So my resistance is going to be rho L over A, which is just L1 plus L2 over A, which is rho L1 over A plus rho L2 over A, which is just the resistance of this part plus the resistance of this part. It's not an earth-shattering concept, but what it tells us is that that is series, because any current flowing in here has to flow through there. There's nowhere, that's just where I'm differentiating between the two resistors. There's nowhere for current to veer off somewhere else. So for resistors in series, the equivalent resistance is just R1 plus R2 plus whatever the resistors are. Resistances. So this is the equivalent of having a 12-volt battery here and a 7-ohm resistor. And so now I can figure out the current because, well, I know what the current flowing across here is. I know the voltage drop across that is 12 volts. And so my current is 12 volts divided by 7 ohms, which is 1.0 activate something. Whatever it happens to be. Amperes. I can now figure out how much potential drop is across each resistor. Because I have, the whole thing is a series circuit, I've got 12/7 of an ampere flowing around it. There's no place for the current to split, so I know across here I have 12/7 of an ampere, and across here I have 12/7 of an ampere. I can now find the voltage drop across here by just doing current times resistance. So my voltage drop here, going to the right, sorry, not voltage drop, potential drop, or the voltage going to the right, is going to be 36/7 volts. And going across here, negative going in that direction. And the potential drop across here, going to the right, be negative 48/7. And just to make sure we didn't make a careless error, negative 36/7 plus negative 48/7 is negative 84/7, which is negative 12, which is what I would expect. Recognize that this is the opposite this is not the same thing as capacitors in series. Capacitor in series, you're adding up the reciprocals and then taking the reciprocal of that sum.
So capacitors are storing charge, resistors are slowing down charge.
They both, yes, in essence, that's the purpose of them. A capacitor in itself will start out with accepting the charge very easily, but then the more charge you build up on the capacitor, charge will start to slow down. Current will start to drop off.
You said before the current is the lack of electrons.
The traditional current is moving opposite direction of electron flow. So as the current's flowing this way, but the electrons are flowing the other way.
Why do we look at the current more than the electrons, where the electrons are going?
Tradition. That before they even knew about electrons, they had developed all the math that go along with current, assuming current flows downhill. And then later on, when they figured out, oh, it's really electrons flowing. They
Think about it as current, like the positive and electrons with a negative.
Yeah. Yep. And what's really happening is that there's a space for the electron to go, so there's a hole here. So the electron jumps into the hole, creating another hole, so an electron, well, probably better start over here. The electron jumps into a hole, creating another hole, another electron jumps into a hole, creating another hole. And so,
Hole in what? What is it exactly?
a hole, just a space in the electron sea where an electron could go.
So current isn't actually anything physical, really, it's just a measure of
It's a measure of charge flowing.
where the charge was or something.
It is, where the charge was.
I mean, because you can measure the electrons, those are like physical things, but like current seems like the lack of something.
It's a measure of how the charges are, it's a measure of the movement of the charges. So I would view measuring current similar to measuring a car's movement. I mean, if you had a speed gun, that analogy could fall apart quickly. Because when you're dealing with the speed of a car, you're dealing with basically how many meters it travels each second. When you're dealing with current, you're dealing not with distance, but dealing with charge. You're just measuring a different thing moving with time.
Either way, you're measuring electrons, though.
Well, I would differentiate that you're not really measuring electrons, you're measuring charge of the electrons.
Okay.
Now the question, are they so linked that measuring one is measuring the other? I would say no, because you can have positive, it is possible to have positive charge flow. It's not everyday experience. Usually it's the electrons flowing. But in high energy experiments, you get protons up to a high speed and smashing into something, so the charge in that case would be based on positive charge flow.
And negative current?
No, it would be positive current.
No.
Protons flow in the direction, you assume protons will flow in the direction.
Oh, because this is positive current.
Yeah, regular current, normal, traditional current flows in the direction of, in the hole analogy, direction of the holes. Thus, and I know I mentioned it in the subclass. I have seen that some people talk about hole movement as opposed to electron movement to represent the current.
Is the positive terminal always gonna be on the left? Or is it-
No, it's always where the long one is.
Yeah, that's what I meant.
I
Do you usually put the long one on the left, or?
When I'm doing it on the board, yes, I usually do that. On a test where I can just easily flip it and I don't have to change my mind,
But in real life, do they do that a lot?
No.
Depends.
it depends. Trying to think of schematics that I see and how they have this situated.
But the direction of current always starts at the longer one, the positive.
Yes.
Yeah.
Because that's the positive side. And
And that's gonna decide on the positive or negative, not whether it's clockwise or counterclockwise or whatever.
Yes, that's correct. Other questions? All right, resistors in parallel. So I got it right there, I've got my resistor, there's my 3 ohm resistor, and now I've got a 4 ohm resistor. And I want to figure out what's the current flowing across each, or first, actually, what's the equivalent resistance? Well, I know that I current flowing up to here, and it's gonna split. I have a junction, place where current can flow one way or the other. I know most of the current's gonna flow, more current's gonna flow across this one than that one, because it's the path of less resistance. So if I go this path right here, I'm gonna lose potential across that, get back to 0. So if this is a 12 volt battery, I'm going across this way, I'm gonna lose 12 volts going across the 3 ohm resistor. I'm also gonna lose 12 volts going across the 4 ohm resistor. Part of what in parallel means is it's the same potential difference across both, between junctions. So my current flowing across here is gonna be 3 amperes. My current flowing across here is gonna be 4 amperes. So if I've got 3 amperes flowing up and 4 amperes flowing to the right, how much is flowing in? Sorry?
7.
Yeah. And that's Kirchhoff's junction rule or current rule. Whatever flows in, flows out. So if I have 7 amperes flowing out of a 12 volt battery, what is the equivalent resistance? In other words, if I had to replace that with a single resistor, I have 7 amperes flowing out, 12 volt battery, trying to figure out what that resistance, the equivalent resistance is. Well, that equivalent resistance is going to be 12 divided by 7. Again, Ohm's law, delta V equals IR. I know that I'm going to lose 12 volts going across that, and that's going to be equal to 7 amperes times R, or R is 12 sevenths ohms. If we make it just slightly more generic, I've got some battery here with some delta V, let's put DS for power supply. I have R1. I have R2. I know the current flowing across here is going to be delta V over R1. Delta V DS. And current flowing across here, it's gonna be delta V ds over R2. That's the current flowing up and the current flowing to the right. So the total current coming out, I total, or let's just write IPS for, it's the current flowing out of the power supply and into the power supply, is going to be delta VPS over R2 plus delta VPS over R1. And that's gotta be equal to the voltage of the power supply over my equivalent resistance. If we cancel out those, we get 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus however many you have in parallel. So the math is the switch between capacitors and resistors. This, replace the R's with a C, and this would be adding capacitors in series. With resistors, it's adding resistors in parallel. Questions here?
That's similar to capacitors then?
Yeah, I view it as it's the opposite of capacitors. So resistors in parallel and capacitors in series have the same math. It's 1 over the equivalent is equal to 1 over the individuals.
Okay.
And then resistors in series and capacitors in parallel, you just add them. On more than one test, I've given a problem with capacitors or resistors and find the equivalent capacitance or resistance. And now, assume all the capacitors got replaced by resistors or vice versa. What's the equivalent now? It is, but some students get it backwards. All right, so the concept question here. When I had just the 3 ohm resistor, I had 4 amperes flowing out. Over here, I added a resistor, and now I have 7 amperes flowing out. So by adding resistance, by adding a resistor, by adding a resistor, I increase the current flowing out of the power supply. How does that make sense? Why does adding resistance, probably better wording it, why does adding a resistor cause an increase in current flow? Yeah, so why, conceptually, why would that increase current flow by adding a resistor in parallel?
Well, I'm asking, is it only happens in parallel, not in series?
Correct. Adding a resistor to reduce resistance. Why does that make sense?
Inverse relationship at the same time.
Yeah, but why does it, again, on the concept side, I feel like you're shooting for the math there. If there were a fire in the room, let's put it in the corner, Brian starts a fire.
That makes sense.
What is going to be the biggest obstacle for our getting out of the classroom? So I heard door twice.
Tables.
Let's simplify it. Let's just get all the tables off to the side. Tables are not gonna, when Brian starts a fire, the tables will
Yeah,
not be
it's everybody trying to go out the same door.
Okay, so the resistance, so the skinnier the door, the greater the resistance. The harder it is to get through. But suppose we open up another door. So we have this one that maybe 2 people can get through at a time, 3 if we're lucky. But we open up one over there that's just really skinny, but it's still open one over there. Are we gonna get people up faster? Yeah. So by adding something with resistance, what do we actually do there? Yes, we open up another pathway.
Increase the flow, increase the, I just want to think, what are the words C word is? Current.
Okay, oh, that's the word. What I'm heading towards here is that before the other door magically appears, what is the resistance of getting through the wall?
Very high.
Yeah. So in this case over here, if you think about it, I'm adding a resistor to drop the resistance. For me, it has conceptual issues, but if you think about, I got two paths here. I got this path across the 3 ohm resistor, and then I have this path right here with an infinite resistance. Then by adding my 4 ohm resistor, all I've done is I've decreased the resistance from infinity to 4. So adding a resistor creates another pathway so we can get more current out. And, well,
Yeah, I think the fact that it's called a resistor is what makes it hard to conceptualize, because like it feels like just like adding a resistor would mean you're like adding more prevention of something, or whatever. It's called a resistor, not a door, you know, or whatever.
an electrical door. Perhaps one of you will get into a position of power and change that.
Yeah, I might have been able to figure that out actually if I just said, if it was called doors, like.
Yeah.
You'd said
That-
door and like add another door.
All right, so that's adding resistors in series, adding resistors in parallel. We are now at a point where we can start doing more complex problems. And then, and I know we're probably not gonna get into any more calculus today, so I'm sorry for that. Or we could go for an RC circuit now and save the more complex resistor series circuits for later, if you want calculus, if you're doing some more calculus right now. But in the absence of a groundswell.
These are DC circuits, what we're learning right now?
Yes.
Okay.
We don't get to AC for another couple chapters. Let's make it